Hi everyone, in this we will understand how to implement a leading one detector or LOD for an 8192-bit input. The main idea is to break the large input into smaller blocks, process them independently and then combine the results. Let's go through the implementation step by step. First, we divide the 8192-bit input into smaller blocks. In this example, we choose a block size of 128 bits. Since 8192 divided by 128 equal to 64. Therefore, the entire input is divided into 64 blocks with each block containing 128 bits. Next, each 128-bit block is processed independently. For each block, we generate two output. First, we generate a valid bit. The valid bit indicates whether the block contains at least one logic 1. It means if valid I equal to 1 means the block contains at least one logic 1. This one logic number 1. And if valid I equal to 0 means the block is completely 0. Second, if a block contains a 1, we determine the position of the leading one within that block. This local position is represented by ID. Since a block contains 128 bits, we need 7 bits to represent the position. Therefore, ID is a 7-bit value. After processing all the blocks, we have a total of 64 valid bits. These valid bits are fed into 64-bit priority encoders. The priority encoder identifies the highest priority block that contains a logic 1. The output of the priority encoder is called block select. This block select indicates which 128-bit block contains the overall leading one. Since there are 64 blocks, block select requires 6 bits. And finally, we combine the block number and the local position within the block to obtain the overall position of the leading one in the complete 8192-bit input. The final index is computed as block select multiple 128 plus ID. Since 128 equal to 2 power 7, therefore multiplication by 128 can be implemented efficiently using a left shift operation. Therefore, final index is equals to block select left shift by 7 or ID. This operation efficiently places the block number in the upper bits and the local position in the lower 7 bits. As a result, the final index width become 6 plus 7, which is 13 bits, which is exactly the number of bits required to represent any position in an 8192-bit vector. This approach significantly reduces complexity and improves scalability for very large input sizes. Thank you for watching. See you in the next video.